moment of inertia of composite areas. All right. Now, I don't get into too details about composite areas. We already talked about composite areas when we were talking about centroids. Right? A good example of a composite area would be cross-section of a beam, like the beams you've seen in steel structures when you see the building a building or a house, or wooden beams, depending on what kind of house you see the building, or what kind of area, what area you are in. You've seen these beams. Let me just draw some simple beam cross section, something like this. You've seen probably these W beams. And what that is, well, if you extend it this way, you will see it like as a beam like this. Like this, and then like this, right? That's a beam, simple beam with it's a W beam, they call it, based on the shape of the cross section. And this is cross section. Now in engineering, there are so many, as I said, you need to find this area moment of inertia, because this area moment of inertia comes into play when you're calculating how can you, how much load this specific structure can handle under different conditions, the equations you have there based on the theories that they're derived. You know, it gives rise to this area moment of inertia formula, or Ix, Iy, or polar moment of inertia. All right. So we need to be able to, the bottom line is, we need to be able to find the moment of inertia of composite areas. This is an example of a beam. There are different shapes of beams. Again, I bring up the example of beam because beam is the most common place that in engineering, at least, you will see you have to deal with. We have also these beams, right? Again, depending on what you're trying to build. This also has some area. These are the areas we're talking about when we talk about area, composite area. These are the common one, but any composite area, right? We should be able to calculate moment of inertia of any composite area given a table with information about some simple ones, like circle, triangle, semicircle, whatever we have in that table. So I just wanted to put in some few words, and then we'll stop at that one. A composite area, we did talk about this, but it's good to re-emphasize, consists of a series of, let me see what I have here, connected simpler parts or shapes, such as of, so say, rectangles, I'm really writing it bad now, such as rectangles, triangles, of circles, and etc. Semicircles, whatever. If we know the moment of inertia, we know the moment of inertia about inertia, let's put it this way, of each of these parts, right? Moment of moment of the composite area, moment of inertia of, let's say, the composite area about an axis, about an axis can be found by, I'll call it algebraic sum, right, plus or minus, of the moments of inertia of all these parts. Right. How do we achieve this? First, we need to learn about parallel axis theorem, what it is, how can we use that to actually go from knowing the area moment of inertia of a part, or how can we use that to move area moment of inertia to different axes, because that's what happens. We have to move it, what we have in the table, we have to be able to move it to be able to calculate the area moment of inertia for the composite area. So we start with parallel axis theorem in the next class. We see what it is and what it says. We look at a couple examples on that, maybe one or two examples on parallel axis theorem, and then basically the examples of parallel axis theorem along with how can it be used to find the moment of inertia of composite areas. All right, let's put it under parallel axis theorem. All right, so let's just do it this way: parallel axis theorem. All right. What does this tell us? So parallel axis theorem is basically the theorem that helps you to find the area moment of inertia of a shape about an axis, knowing its area moment of inertia about a different axis, as long as these two axes are parallel. So say it again. Parallel axis theorem helps you to find, or gives you an explicit expression to find the area moment of inertia of an area, or moment of inertia of an area about an axis, as long as you know the area moment of inertia of that area about a different axis, and as long as these two axes are parallel. Right? So it's more like, you can think about it as transferring the axis to a different place, if you want to think about it that way. So let me just give you the theorem itself. Right? It says here is the theorem, or better to say, the moment of inertia about an axis is equal to its moment of inertia about a parallel axis plus the product of the area and the square of the perpendicular distance between the axes. So here's what it's trying to say. Let me try to draw it here. And here's, let's call this X and Y. I'm going to draw some rigid body, like a potato shape kind of thing. I'm going to put the next axis here. I'm going to call this Y prime. Y prime is parallel to Y and X prime is parallel to X. All right. This is point C. I'll call this distance. And this distance. All right. Let's call this distance dx. This distance dy. And we can always go with this as d. Basically, we have two sets of axes. X-axis are parallel, y-axis are parallel. All right. And we can think of this as some element there. All right. This is dA. So this is X prime. This is Y prime. Now, parallel axis theorem, says, well, if you know the moment of inertia of for this rigid body about X prime and Y prime, you can find the moment of inertia of rigid body about X and Y as long as they're parallel to their X prime and Y prime through this expression. So Ix, or better to say Ix is equal to Ix prime plus A area, product of the area and the square of the perpendicular distance. Perpendicular distance, we're looking at X, would be dy square. Moment of inertia about y-axis. As long as you know the moment of inertia about y prime, you can find moment of inertia about y by adding the product of area and the square of the perpendicular distance between y and y prime, which we call it dx here. The same story for polar moment of inertia, right? J O about point, call this O, and this is C, is equal to J C plus A D squared. This is what parallel axis theorem says. I can put all of them in one box. So knowing the moment of inertia about an axis, you can find the moment of inertia about a different axis parallel to that axis, as long as you know the area of the surface and the distance between these two parallel axes. All right. Now, if just a note, if the axis like X prime and Y prime pass through the center of gravity, so if C is the center of gravity, you will see that they use a bar at the top of, they do it this way, bar, and bar. So say Ix prime bar, Iy prime bar, Jc bar. If C is the center of gravity, that's more of a notation thing. If the center of gravity, or centroid, we have to say. So if C is the centroid, where the center of this area is, if the axis that you have the information about or you're looking at are passing through the centroid of the area, then you will see they put a bar on top of this, just a notation. Also, you can, from these, we can conclude that for radius of gyration, we can make this, just plug these values from the original equation, and you can see that kx is kx prime bar squared plus d y squared, and ky squared is ky prime bar squared plus dx squared, and eventually ko squared. This is for radius of gyration. Similarly, you can just, I'm trying to say that you can, from these and plug them into the original equation, the definition of radius of gyration, and do the math, you can actually get the set of equations on the right. These are also relationships between relation between the radius of gyration for the original axis and the new axis. That would be kc bar squared plus d squared. Right, just keep these as side notes. These are like byproduct of parallel axis theorem, or not byproduct. You can just find those based on the relationship between radius of gyration and